Okay, this is the read flow of HDFS. So when the client goes and opens the connection with the distributed file system is one of the files in the library that you get with Hadoop. And in that library, the distributed file system class will go and talk to the name node to identify the addresses of where the blocks of that file are. As I've explained previously, the name node keeps the block information of a given file because it has the file metadata. From the file metadata, it will identify where each block location is, and it will return the list of the data node IP addresses to the distributed file system. Then the client opens a file system data input stream. The input stream allows it to actually go connect to the nodes and actually read the data. So let's suppose the data is in three locations as explained in this diagram. So it talks to the first data node, reads the blocks, and caches it at the file system data input stream. So 3 streams are running and picking up each block, and all the blocks are put together and returned back to the HDFS client, and the client will close the connection. That's what this diagram shows. At any point in time, none of the data actually goes to the name node. All the name node is doing is controlling the system. It's not managing the data blocks through it. It always tells the client what to do. So that's the most important thing that you need to understand. The name node is already very busy. It has a huge file system tree that it's managing. It's managing all the data nodes. It's managing the replications. It's managing all the behind the scenes work that we are asking the name node to do. So it doesn't ever let open the stream to the name node to store the data, or it never lets the data go through the name node. So that is something you have to remember. It's only the control plane. It's not the data plane. So that is the read part of the name node. The next one is the write part. So how does the write happen? It's the same situation where the client opens a distributed file system when it talks to the name node. Here it computes how many blocks it needs to do. So in that 500 megs example, I need to create 4 blocks. So the moment I say I need to create 4 blocks, the name node gives 4 locations where the data blocks need to go. And then also the replication blocks that the data needs to go. So when the client now opens a data file output stream. In this output stream, it puts the first block into the data node, and this data node, using the data streamer, puts the replication packages into the other data nodes. So if you see, there is a streamer going on wherein there's a data streamer class which is actually doing that, but it's doing the replication behind the scenes. So every block goes through a replication and actual first copy and then the replication, if you see this flow. So the most important thing is, are all the replicas successful? Maybe and maybe not. When the name node is satisfied that it can replicate the block even after the failure, then it doesn't worry about the replicas being successful, and it returns the ACK saying the acknowledgement saying that, hey, I'm good to go. Let the client know that it's been done. So there is a certain criteria inside the name node saying that after a certain point, if the replication is successful or not successful, it has that criteria, and it will say, oh yeah, I'm fine. Go ahead and say the file has been copied. So again, in this case, the name node decides which data nodes to go to, but the file never reaches the name node. The file from the client goes directly to the data nodes into those blocks. So that is something you have to remember. The name node is very, very busy. It's in the control plane. It's not in the data plane. Okay, so let me go back to the questions. Do we need to stop the cluster to add data nodes? No, we don't need to stop the cluster to add the data nodes. The moment you add the data nodes send their heartbeat to the name node and the block report. Based on the block report and the heartbeat, the name node adds the data nodes to its cluster. So you do not need to stop the cluster. How does the name node know if the data node is alive or dead? It's the same thing. It sends the heartbeat. It sets heartbeat at a certain interval every time to know that the data node is alive. If the heartbeat, it doesn't receive the heartbeat, then it identifies which blocks are there in that data node, and it'll start a replication of those blocks in other data nodes so that you do not lose the data. If the block gets corrupted, how does the name node know? The name node knows if a block has been corrupted. If the block report is doesn't contain the data block. Every block has a CRC code, like a checksum code, to identify if the integrity of the data has been managed or not. If any of those codes got corrupted, or if the data block is not being returned, then the name node knows that the block is not available, so it again restarts the replication. How does the replication happen once the file is uploaded? Once the file is uploaded, as I've shown in this diagram, there is a streamer that runs, which actually sends the replication to the other data nodes, if you can see this. And this has been done by the data streamer. So you don't need to go into the details of the data streamer, but that manages the copy. Again, the name node is not doing the work, it's making the data node do the work, but actually based on the block reports, it identifies if it's successful or not successful. If it is not successful, it again starts another copy. So that is where there are journals and journal nodes and a lot of other nodes that are available. It manages it through all those information. This one. How does the replication happen? How many blocks are created for 500 mega file if the replication factor is 3? So there are 4 blocks and the replication factor is 3, so it's 4 3s are 12. There are 12 blocks that are created, not 4. Because your replication factor is 3, you have to also calculate the replication factor. So at the end of the day, there'll be 4 blocks with 1 block having a minimal size, and that multiplied by 3, it's 4 3s 12. 12 blocks are created. Does the client upload the file to the name node or data node? The client always uploads the file to the data node. The name node is only telling the client to which data node it needs to go to. It doesn't actually, the client will never send the data anytime to the name node. Sorry. How is the map job different from the reduce job? The map job, what it does is it makes sure that all the raw data that has been fed to the map reduce program is converted to a form which can be computed and processed by the reduce job. So what the map is actually doing is preparing the data, and what the reduce job is doing is making the results the way it needs to look for the end result to look. So it's converting the computed value and to the end result what the user is expecting. So the map is actually preparing, reduce is actually doing. Why do you think map cannot run on blocks directly instead of input splits? Blocks are physical. Blocks do not understand line splits, or they do not even acknowledge if there is a line that's been cut in the middle or something like that. Input splits are actually, they understand where the line ends based on the input format. So you have an input format for a file, and that input format will help you to know where your lines have ended. So certain blocks might not be complete. So it goes and gets the next block's information so that it can complete the line and provide it to the map program. That's the reason it's very important to know that blocks are physical storage inside HDFS and input splits are logical splits which are used for the map program. How are the objects of the same key sent to the reduce job from all the map jobs? That is sort and shuffle, as I've explained. All the keys are actually sent to the reduce job because there is a certain process that happens in the middle which is called sort and shuffle. When it's shuffling, it's moving all the keys of the same keys of the same thing into to the reduce job node. So the data is moving. So in sort and shuffle, what happens is the map task need not be at the same spot as the reduce task. So what happens in that case is, I'll just show you a small example here. Oh, I have Jan. Okay. So let's suppose here the map job is running and here the reduce job is running and here the map jobs are running. So all the data from this has to move to this container. But what moves to this container, you have to also sort it. So here the most important thing is which keys need to move and how are the keys moving together. So there's a sort and shuffle going on, which sorts it and actually sends it to the appropriate reduce jobs. So that's the most important thing to understand in a map reduce program. So I don't know if you remember, if you've watched my previous videos, but there is very clear explanation of how the sorting and the reducing happens. But if you have more questions, I'll explain it in the next sessions. What is the difference between fs image and edit log? Fs image is the first thing that the name node reads in the safe mode. When you start your name node in the safe mode, it always starts in the safe mode, and what it loads in memory is the file system image. And after that, if there are any edits or anything of that sort, that goes into the edit log. And what the secondary name node does in the whole process is to reconstruct the file system image so that you don't have so many adds and edits. So that is what the secondary node keeps doing, so that your file system image is up to date. So when the name node crashes again and it's brought back, you don't have to go through the entire file system image and edit log. It's already updated into the file system image. So these are the questions, and I have one more thing to explain, which is the yarn, and then I will take questions. So these are the things that I explained in my previous session, but I wanted to go in detail about a little bit of yarn so that you understand why we need yarn. Yarn, I didn't have any questions in the assignment for yarn because I wanted to again explain it and then give you folks an assignment. So the clients always submit jobs to the cluster. But how are the jobs executing? There is a process to the job execution. So that is managed by the resource manager, and the resource manager has three parts. One is the resource manager, scheduler, and the application manager. So the resource manager of Yarn does three things. One, it makes sure that it knows how much compute is available for it, how much memory is available for it, and how many nodes are available in the cluster. So those are the three pieces of information it needs to know. The next one is a scheduler. Scheduler is the one which actually schedules the job into the cluster. So what if the cluster is full? What if you do not have enough user quotas? All that stuff is actually managed by the scheduler, and it launches the jobs when it's available, and it is processable. So there's a fair scheduler, there's a capacity scheduler. Fair scheduler means everybody has the same quota and they can actually schedule the process. Capacity schedulers, you have quotas, because it's a multi-tenant system where every tenant has its own quotas and capacities. Based on your quotas and capacities and your priorities, the capacity scheduler will schedule the jobs. So that's what the scheduler does. The application manager makes sure that you launch your applications and run the applications. So when you are running a typical MapReduce program, there are three parts to the program that you need to understand. One is the driver. Driver is actually the list of things that you do in a MapReduce. So it's actually it's actually writing down all the points that you need. So what you're telling is run this map, then run this reduce, then run this, run that, run this. All the list of things that need to be done is actually in the driver. The second part is the mapper and the reducer. So all the mappers execute first, and then the reducer executes, so that whatever is computed, whatever is prepared can be computed. So usually it's always a map and a reduce that runs, and you can have chains of maps and reduces, or chains of maps and chains of reduces. So in this diagram, as I've explained, as you can see, there's a resource manager here, and it talks to the node managers. The node managers, what they do is they communicate the resource availability. What is the node status? What is the resource availability? All that information they will tell the resource manager. And when the job is being submitted, the application manager, it launches an application master. What this application master is executing the driver program. So when the driver program is being executed, this goes and says, hey, I need 5 maps. Hey, I need 4 maps to execute. Then this one then finds all the containers that are available to run the mappers or the reducers. So when it says I want 5 mappers, it goes and identifies where the 5 mappers are. And then all those containers get launched. And once the containers get launched, the containers are explaining the application master that my map is complete. So this is the map reduce status. This is telling you that, okay, this map is, if you're running 5 maps, so if you have 5 containers here, these 5 containers tell the application master, okay, this map is complete, this map is complete, this map is complete. So once the map's complete, then it needs to run the reduce. So then this application master goes and again and tells the resource manager, hey, I need to run six reduces. So then again, it goes and finds the containers to run the it finds 6 containers to run the reduce programs, and these reduce programs again send back the status to the application master saying that, hey, I'm done with these reduces. And at the end, once everything is finished, the application master like closes and it's done, and the program's complete. That's how the entire chain runs. So I'm going to stop the recording and I will take questions now.